Another power index is the Shapley-Shubik power index. This one looks at coalitions also, but instead of worrying about people joining, they actually consider it sequential coalitions. So they actually consider every player being in the coalition together. That's not really what happens in reality, but this is how they figure out their power. But they worry about what order they actually join, because they consider it kind of like whoever joins first is really for it. Later, people may not be as much for it, but so you have more power if you're joining early on. And so let's say we look at three players. Player one joins first, then player two, then player three. That is one coalition you could have. But you could have another coalition. You could have player one joining first, then player three joins, then player two. Another coalition could be player two joins first, then player one, then player three. Another one could be player two joins first, then three, then one. And then player three could join first, then player one, then player two. And then three could join two, then one. When you have three players in a weighted voting system, this is always your coalitions. So you don't have to actually think about how to write them each time. This is always what they're going to be. The number of sequential coalitions is n factorial, because if you think about this, three players, 3 factorial is 6, and notice there are 6 coalitions. So the number of sequential coalitions is n factorial. Notice with the sequential coalitions, we used, instead of a parenthesis, we use this kind of weird less than and greater than symbols. That kind of shows people, hey, this one is a sequential coalition and not just a regular coalition. So instead of using the braces, we're going to use these things. So you're going to have the number of sequential coalitions is n factorial if you have n players. So if you have n equals 3, you have 6 coalitions. N equals 4, you have 24. Notice n equals 5, you'd have 120. So these get really big really fast, but you don't have to think about what ordering to put them in, or not ordering, but which ones are winning or losing. At the start, you just put them down. What is interesting in these is that we're actually going to look now at what we call a pivotal player. And a pivotal player is the person that when they join the coalition, they make it from losing to suddenly winning. So like if we have this 3-player one here, again, your sequential coalitions are always the exact same, then we can try to figure out, okay, what's happening. We need 6 votes to win. If we have player 1 has 5 votes, it's not winning. Player 2 now joins, and it suddenly becomes a winning coalition. 5 plus 2 is 7, which is more than 6. So player 2 makes it winning. We don't care about player 3. Player 2 is what made it winning. In this coalition, 1, then 3, then 2, player 3 joining makes it suddenly winning. In this one, player 2, then player 1, then player 3, player 1 joining makes it suddenly winning. 2, then 3, then 1, again, player 1 joining makes it winning because 2 and 3 together only have 3 votes. Player 3, then 1, then 2, player 1 again makes it winning. Player 3, then 2, then 1, player 1 again is what makes it winning because 2 and 3 together can't make it win. So we'll circle all the ones that are winning, and then we're going to count how often is each one what we call a pivotal player. So player 2, well, let's start with player 1. Player 1 is 1, 2, 3, 4 times that player 1 is in fact pivotal. So player 1 has a 4 on the top. The denominator is 6 because there are 6 coalitions, sequential coalitions. So it's 4, 6. Player 2 is only circled 1 time, so player 2 only has a 1/6 power. Player 3 also is only 1 time, so 1/6. So 67, 70, 17, and 17%. Notice player 2 actually has player 2 and 3 have the same power, but they don't control the same votes. So your number of votes you control doesn't necessarily say what power you have, but the number of times you're actually pivotal is what considers that. And that's how the Shapley-Shubik power distribution works.